Good morning, everyone. Right off the bat, we have a vocabulary word to add to our purple sheet. Go ahead and take those out. Add this definition. And if you have lost your purple sheet or need another one, ask the adult in the room. We will pause right here to give you a chance to write this down, and then we're getting started with the notes. Our notes for today is going to include finding another way to factor when polynomials are not factorable using division. And the word of the day is rational because we're going to be talking about rational zeros or rational x-intercepts. And according to our definition, rational means a number that can be written as a fraction. So it is possible to get some fractions today, but what we won't see are repeating decimals and square roots and complex numbers. So first, since division is going to come up today, we're going to practice division. At the beginning, we're going all the way back to, I think it was third grade when you first learned long division. And the reason we're going to practice long division with numbers is because that pattern of movements is exactly the same as how you would divide polynomials. So first, when you're doing long division, we're going to check if 16 goes into the first digit, which is 3. How many times does 16 go into 3? None. So we skip that number or put a 0. So then bring in the second digit and keep asking that question. 16 goes into 30 one time because 2 times would be too big. Next, we multiply 1 times 16 and write down that number underneath the 30. Next, we subtract. And if we did that correctly, this number should be too small for 16 to go into it. So we bring down the 1 to continue division. 16 goes into 141 about 8 times. I tested this with my other classes, and if we did 16 times 9, it was just too big, just slightly too big, so we're going to go with 8. Multiply the 8 times 16 to get your next row. And then subtract. And since we are working with polynomials later, we're going to avoid decimals at this point. In elementary or whenever you learned about decimals, you were probably told to put a point, 0, and then keep pulling down numbers until you just run out. We're going to stop when we get a remainder because that's going to be part of the instruction today as well. So what I do want to summarize this with is that this whole division problem means that when we divide 301 by 16, we are left with 18 and 13 units still waiting to be divided by 16. So this can be rewritten as 301 over 16, that's the division, is equal to the quotient plus the remainder over the divisor. You're basically saying 13 still hasn't been divided yet because I stopped early, so I'm going to write that it still needs to be divided. Okay, we're going to do that exact same process with long division of polynomials. It has the same steps. The only downside is you're working with x's. So when we're saying how many times does 16 go into 30, we're going to do that a little bit differently with polynomials because it doesn't make sense to say how many times does x go into x squared. Okay, so first step is to take the first term and divide. And like I said, we're not going to ask how many times does it go in. We're going to say x squared divided by x, which is equal to x. So on top, we're going to put x. Next step with numbers was to multiply down the number that you just wrote on top times the number on the side. So I'm going to multiply x times x plus 2 to mimic what we did with long division earlier. X times x squared and x times 2. Next step in long division was to subtract those 2 rows to see what you have remaining. X squared minus x squared is 0. 3x minus 2x is x. And before we start our next round, we bring down the next digit. and then we repeat. So now I'm asking the question, x divided by x, which is 1, positive 1. So I put a 1 on top, and just like we did with long division, we'll then multiply only the new number times the divisor. So 1 times x plus 2 gives us the next row, and then you subtract. X minus x is 0, and 2 minus 2 is 0. So this time it looks like we had no remainder. So I can rewrite this as x squared plus 3x plus 2 divided by x plus 2 is the same thing as x plus 1 plus 0 remainder. And this is kind of the key to what we're going to be doing today. Whenever we get a 0 remainder, it's going to help us to factor because I can now rewrite this expression that I just wrote by multiplying both sides by x plus 2. And I get factors for x squared plus 3x plus 2. So watch this happen as we move the x plus 2 to the right side. That stuff on the right-hand side is the factored form of the expression on the left-hand side. We could have found that ourselves. We know how to factor. We've practiced that. But you can see I also got the same result through division, which is going to be the key today. Keep in mind, the examples we're going to see today are polynomials that you cannot factor using traditional methods. So I'm not just adding work to your load. What I'm doing is giving you an alternative method that will work if all other methods fail. Now, of course, what I just did was kind of long and tedious. So there is a shorthand for division, and this is going to be my preferred method because we're going to do so much division that it is just not worth it to do long division every single time. So what I have over here is synthetic division, which most of us should have seen before. So we're just going to go through the motions and practice it. The setup initially is that we take the coefficients from the thing being divided and write it on the top row. So you'll see that I'm using the exact same numbers we had in the last question across the top row. Then the number in the box is the 0 of the divisor. So it's the thing that you would get from x plus 2 if you set it equal to 0. That means it's also giving us the x-intercept. It's going to be very useful later. Okay, now that we have it set up, the process is bring down the first number, don't do anything to it. Then you're going to multiply the 0 times that number you just wrote down. So negative 2 times 1 gives me the next digit in the row. Then we add down between these two rows. And then you repeat by multiplying again by your 0 to get the next digit. And then you add again, and you would keep doing that until you run out of digits. The last thing you write down is always going to be your remainder. The next number in line will be your constant. The next number in line will be an x, and then the x power would go up however many times it needs to fill in every single number. Our answer is just 1x plus 1, which is the same answer I got through long division, but this was significantly shorter. Okay, let's go ahead and look at our first step when we are using division to help us factor polynomials that we can't factor any other way. This first step is going to feel like I'm just asking you to do something really tedious and there's no point. So just bear with me through this first part and then we'll get to what you're going to do with this information. So I'm not going to address the rational zeros theorem. First, let's just look at the parts that are blue and red. So it says that we have values of p. P is a factor of the constant coefficient. What that means is the letter p, which I'm going to call it p's and q's, the p is the list of all numbers that divide the constant in our polynomial. Q is the list of all numbers that divide the leading coefficient, so the number in front of your highest power term. Okay, let's try it. Here's our first example. I am going to actually edit this example real quick because this number is huge and it's going to make a very long list. So let's change the 36 to a 10 just to make our lives a little bit easier. Okay, so P was the list of all numbers that divide the constant at the end. So we're thinking of all numbers that divide into 10. So I'm just going to list them by thinking of things that multiply to 10. So I have 1 and 10, 2 and 5, and I'm out of numbers. Also keep in mind, negative numbers can also divide 10. Even though 10 is positive, I can divide it by something like a -1. What I'm looking for is numbers that can divide into 10 and not create decimals. Negatives would not do that. So what I'm going to do is actually adjust my list and say plus and minus of each of these numbers will work. Next, we're going to list all of the Q's. Q represented the factors of the leading coefficient, so 4. So we're looking for all numbers that factor 4. I have 1 and 4, and 2 and 2. Okay, last step was to combine P's and Q's together into a new list. This new list is made up of all the P's divided by all the Q's. So we're going to do that very carefully here, one at a time. I'm going to take the first P and divide it with all of the Q's. So the first number I get is 1. Next number I get is 1 over 2, then 1 over 4. And at that point, we have divided 1 by all of the Q's. So we are done with 1. Next, we're going to take 2 and divide it by all of the Q's. So 2 by 1 is 2. 2 by 2 is 1, but we already wrote it, so you don't have to write it again. And 2 by 4 is 1/2, which we also already wrote. So we're done with 2's. Then we move on to the next number. 5 divided by 1, 5 divided by 2, and 5 divided by 4. Finally, ending with 10. 10 divided by 1, 10 divided by 2 is 5, which we already have, and 10 divided by 4 is 5 over 2, which we already have. So this is our complete list all the way through. And you're probably still wondering, why the heck are we making this list? Bear with me, almost there, very close to answering that question. I want you guys to try that same process with this next polynomial just below the one that I just did. The P's are based on the number -8, and the Q's are based on the number in the very front. Think to yourself, what would the number be in the front if there isn't a number in the front? 1, that's right. So our Q's are based on the number 1, which means the only factor is 1. So we already have half of this done. You guys figure out your P and then sort out your P divided by Q list. Okay, here is my list of P's and P over Q's. This one worked out really nicely because Q was just 1, so if we divide all the P's by all the Q's, we just get the list of P's back. Okay, so now let's actually talk about why we're doing this. So back up here, the rational zeros theorem says if we have a polynomial and it has integer coefficients, So very specific polynomial, but it applies to all the ones we're looking at in this class. Then every rational zero, or as we saw in our vocab, zeros that can be written as fractions, is of the form p over q. So what that means in easier terms is that all of the zeros that this polynomial has that are not complex, they don't have an I, and the ones that do not have a square root, they are all in this list that I'm looking at right now. Now that doesn't seem super remarkable because there's a bunch of other numbers in this list as well, so it's hard to tell which ones are the zeros that we need. But in the next step, we're going to see that basically this method of factoring is guess and check. And if I didn't have a list of potential zeros, we would be guessing and checking any random number that came to mind. So having a list of p over q's means the answer to the question that I'm guessing and checking is somewhere in this list, and I only have to guess and check these numbers. And usually, I would say almost all the time, you would never have to come close to testing all of these numbers. So although the list looks really long, we may be testing one or two numbers before we find a winner. But it's just kind of exciting that we don't have to completely blindly guess to be able to guess and check because we have this list in front of us. So let's test that out. Here's the actual instructions, and if you're going to write down anything today, let it be this. If the remainder of dividing a polynomial by a test factor, so whatever factor you're trying to test at the time when you're doing your guess and check, if the remainder when you divide it is 0, then the thing that you were testing is a factor of p, factorable, and the c, the 0, is a 0 of p, which tells us it is an x-intercept. So not only are you getting factors from this method, you're also getting a list of x-intercepts from this method, which is perfect because we just did graphing last class. So let's test this. Here is our same polynomial we were just working with. I brought down our list of p's and q's that we've already worked for. Let's test these to see which ones are actually zeros of this polynomial. So we're just going to pick any number from this list. I usually recommend starting with positives and starting with the smallest numbers, just because they're easier to work with. So I'm going to start with 1. Let's use 1 in synthetic division, and since we're looking at the list of zeros, we're actually just going to write 1 in the synthetic division. No need to switch the signs around. Then I'm listing all of the coefficients of the different terms in that polynomial as my top row in synthetic. All right, next we're just going through the steps of synthetic. So bring down the first digit without changing it, multiply it by the 1 in the corner, add the 2 rows together, and then repeat. The last digit you wrote down is the remainder, and according to this box above, if our remainder is 0, then the factor you were dividing by is a factor of p, and the 0 that you wrote in your synthetic division is an x-intercept of p. So here's how we're going to use this information for our advantage. We're going to write the thing that we were dividing by, which was x minus 1, and the answer to the division as factors that make up p. So here is the new form of p, partially factored. As soon as you see a quadratic appear in your factoring, you should stop using this method. You do not need to continue testing zeros to split apart this quadratic. You can if you want to, but you run the risk of never finding an answer. Because remember, the whole point of this property was that it only works with rational zeros. It is possible for a quadratic to produce answers that have square roots. If that's the case, you will never find the solutions in this list. So as soon as you see a quadratic, stop doing division. Solve that quadratic some other way. So in this case, it is factorable. Let's continue to factor ourselves. I'm looking for two numbers that multiply to 8 and add to -6. So think about those numbers, and those are going to be in your factor. I got -2 and -4. It is now completely factored. And if you take a peek at the original p of x, that was not something we could factor. When it's got 4 terms, I always think factor by grouping, but if we group these terms into clumps, they will not match when we try to factor by grouping. And so you would have been stuck with this not matching, factoring sort of mixture of terms that doesn't really go anywhere further. So we would have been stuck at that point. Doing this division actually helped us to completely factor something that we couldn't have done before. Exciting. Okay, let's try one more. Here we go. Okay, this one we're going to review everything that we've done today and last class. And then we're at the end of the notes, so you have lots of work time. This is especially helpful if you either missed last class or if you're still working on your yellow worksheet to turn in, then this is a good review for you. So before we even start with the division, here's a couple of tips. If you're going to graph, go ahead and pull whatever information you can from this before we factor it. Y-intercepts, super easy to find if it's not factored, and end behavior, much easier to find if it's not factored. So for y-intercepts, you plug in x equals 0. And the reason that's easier when we don't have it factored is that all those terms that have an x just disappear. They turn into zeros. And so our y-intercept in this case is 4. Very quick to find. The next thing that I said was really easy to find when it's not factored is the end behavior. And that's because it's based on the leading term, which is much easier to find right now before we separate everything out. I see that it is positive and has an odd degree. Positive meant that on the right-hand side, the graph will be pointing up. The odd degree means that the left and right-hand side are doing opposite things. So the left-hand side will be pointing down. You can also use your vocab sheet to help with that. We wrote down a little grid to decide what the end behavior was going to be. Okay, let's go ahead and factor because all we're missing now from our graph is the zeros. And I'm looking at this and I notice again, it's not able to be factored by grouping. If I took away an x squared from the first two terms, I'm left with 2 and 5. But I can't get a 2 and 5 to appear in the second half of the polynomials. So we do have to do division. That is not the preferred method. I would definitely rather do factor by grouping, but it is a good option if you're stuck. So first thing for this to work is we need our P over Q list. So P's come from dividing 4. So 1, 2, and 4. Q comes from the 2 at the front. And then you write your list of P's over Q's to decide what is your potential list of zeros. Going carefully along, I'm going to take each P and divide it by all the Q's. So 1 divided by 1, and then 1 divided by 2. Next, 2 divided by 1. And 2 divided by 2 is 1, so we already have it. Then 4 divided by 1. And 4 divided by 2 is 2, which we already have. So everything is now accounted for. Our list has 4 numbers, plus and minus. Okay, so we're going to pick a digit to start and see if it gives us a 0. I'm going to pick Let's do 2 this time, just because I started at the beginning last time, so I'm just going to pick in the middle. All right, let's try 2. So 2 is a 0. It's going to go in the corner. Then we're going to put down all the coefficients for the entire polynomial across the top row. Then follow through with synthetic division, so bring down the first digit, multiply that times the 2 in the corner. I'm going to let the screen catch up with me a little bit here. Add between the 2 rows, and then repeat. Multiply to the number in the corner, add your rows, and right about here I can tell something is going wrong. I can already predict that the next number is not going to be -4, so we can abandon this as a potential 0. As soon as you know that the remainder is not going to be 0, you can stop. I'm not going to ask you to go all the way through if you're trying to find zeros. So let's abandon this and try a different number, maybe 1/2, because I feel like fractions are going to be a little scary. Let's try it. So I'm going to start over with 1/2. Okay, now that this is set up, I'm going to go ahead and silently work through this. You go ahead and do that on your own paper as well, and let's see if we get a 0. And it looks like we did. I got a 0 for the remainder, which means we found a 0. So let's go ahead and write this down in a factored form, because then we should be able to find all the zeros at this point. The factor that we divided by would be x minus 1/2. And then the quotient is the other factor. The first digit is a constant, then an x, and then an x squared. This remaining quadratic is factorable. It's a little hard to tell because of the 2, but we can take a 2 from all 3 of those numbers. So I'm going to factor out a 2 first and see if we can see how to factor what's left behind. This will simplify the numbers a little bit. All right, and I'm looking for numbers that multiply to -4 but add to 3. +4, -1. So now we have it fully factored. I can also see the multiplicity, which was the power on each factor. They all have a power of 1 because there is no power on each of the factors. And what that meant for our graph is that when we get to those x-intercepts, the graph is going to cross the x-axis at those points instead of bouncing. So I think we have everything and we're ready to sketch. Let me zoom out so we can see all of that information. Maybe, there we go. All right, and sketching. So let's first plot all of the points that we have found. We have a y-intercept at 4, x-intercepts at 1/2 and 1, and -4. The end behavior was up on the right and down on the left. And since our multiplicity is odd, the power on each of those factors is odd, then as I connect the dots, we're going to cross over the x-axis each time we get to a 0. So I'm sketching. We'll see when it loads. One of our warning signs about something going wrong was that if you sketch in your end behavior first and then you go to connect your dots, if the ends don't line up with what you predicted, then something went wrong along the way. Once this graph loads, we will wrap up for the day. You have some work time now. You should try to finish the yellow worksheet. It's not due until next week. However, we do have a long weekend and it is very easy to lose that worksheet. So try to finish it in class today and turn it in. Then you have a new assignment that is based on this division and factoring that we just talked about today. And it is only 10 questions on Math Excel, very doable to finish in a class. And if you finish both of those, you have no math homework at all for your long weekend. All right, enjoy.